Hello, this is Dr. Christy Lukes, and in this lesson we're going to be looking at the most basic concepts of experimental design. Now, if you really want to know more about this, you need a full course in it, and I'm assuming that you have not had that. This is just going to pick up the highlights. So let's just say we wanted to conduct an experiment to come up with the perfect cookie recipe, okay? Now, we've been working all year, we've optimized the ingredients, but now we want to optimize the cooking instructions. So we want to do this, and I just arbitrarily said I want it to cook for exactly 12 minutes. I have a favorite music playlist that I'm going to listen to while I'm baking those cookies, and it's 12 minutes long. But I need to know what size and what temperature to bake those cookies so that I get the perfect cookie, okay, in 12 minutes. So let's just simplify this a little bit by saying, okay, the balls of dough are going to be the 1-inch, little bitty cookies, 2-inch, or 3-inch, those monster cookies. And the oven temperatures I can choose 325, 350, 375, or 400 degrees. Okay. So I could do a tray at 1 inch at 325, one at 1 inch at 350, one at 1 inch 375, repeat, right? I could go through and do this. This would require me to bake 12 different batches and evaluate those, okay? But does that get at what I really want to know, okay? So there are some issues here. If I'm having to make 12 batches, is the dough actually being prepared the same way every time? Is the raw material consistent? Maybe I ran out of brand 1 of honey and I substituted with a different brand of honey. Is that going to make a difference in the final product? Is my oven performing properly? So are the temperatures correct, or is it fluctuating? Do they hold constant? Does it matter what temperature it is outside? Is the temperature uniform at all spots in the oven? And then there's this operator issue, right? Where did I place the tray in the oven? Did I always place it in the same spot? Did I go to a higher or a lower location? Did I push it further in or leave it closer to the door? Those 1-inch balls, were they 1 inch really exactly every single time? How uniform were they? And how consistent was I in where I placed the dough on the cookie tray? Does everywhere on that cookie tray bake evenly? So there are a lot of systematic errors that I might end up encountering in this procedure. So there are ways that I can minimize these issues. Randomization and repetition are the two keys here. So instead of doing all, exactly the same thing in a certain order, I can randomly cook the, maybe 1 inch and 3 inch on the same tray, okay? I also want to do repetitions so that I can make sure that it wasn't just a fluke of, oh, the oven wasn't performing well that time. I want to try it multiple times. So one of the ways that I can do this is through a Latin square design. Now, a Latin square design is a plan, kind of like a Sudoku board, all right? So you're going to lay out the plan for your cookie dough kind of in a special order, okay? So if I have 3 options, so 1 inch, 2 inch, and 3 inch cookies, then I can do, 1 inch, 2 inch, 3 inch, 3 inch, 1 inch, 2 inch, 2 inch, 3 inch, 1 inch, right? Okay, that's the idea of a Latin square. And so that gives you 3 samples of every case, right? So A is repeated 3 times, B 3 times, etc. Okay, and they are in a random order. Okay. And then you could do all of those in the oven at one time, or you could do like ABC in one trial and then CAB in another trial. Okay, so this gives us some ways of doing that repetition and randomization. It's planned randomization, but it is randomizing the placement. If you're only having to change one thing, this works pretty well, but it's not very efficient when you have multiple factors. So if I need to do this for the 325 degree oven and the 350 degree oven and the 375 degree oven, etc., okay, then that's going to not be all that efficient. If you are looking for something where all you want to know is best or worst, one of the things you can do is just simply try, bake 10 cookies, okay, of different diameters, all right, and then rank them. So you're going to randomize and conduct your test for all of these samples, and then you're going to put them in order. And what you do is you look to see how many, so these are, placed in order, treatment B, treatment C, so 2-inch and 3-inch cookies, let's say. All right, and the high end was all the 2-inch cookies, the low end was all the 3-inch cookies, and then in between we have this mess of stuff. So what I do is I count the ends, okay? How many did I have of the case B before I got to my first case C? How many did I have of case C before I got to my first case B coming from the other end? And go through and count those, okay? And basically, the idea is that you're going to look at your end count, and if your end count is more than 6, then the alpha is 0.10, okay? That you have B is, in this case, better than C. If you have more than 7 in your end count, it's 0.05, and so forth. These are your alpha values. And so this is highly significant that case B is better than case C in this case. More of what we are likely to do is something along the lines of factorial design. So factorial design looks at all the possible combinations of the factors and looks at number of replicates I need to do and so forth. So if I have A levels of factor A, so cookie size, and B levels of factor B, oven temperature, every replicate of the experiment needs to contain all of those treatments, okay? So if I have 3 cookie sizes and 4 oven temperatures, then 3 times 4, I have 12 different treatments that I need to do. And then I need replications. Let's say I want to replicate, normally I would say 5 times, but let's go with 3 because that's going to be a really large number already. So 3 times 12, I'm going to need 36 different treatments doing this factorial design, okay? It's a lot of cookies. And then we have issues still of what if I decide that maybe it's not 1 inch, it's 1.5 inch, etc. Or maybe the best temperature was 390, right? I'm not testing every possibility. So this is also inefficient. It gets at what I need to do, but it's inefficient. So we need to figure out what is really the goal of our experiment, okay? Is it that I'm looking for what's the effect of dough ball size and baking temperature on the quality of the cookie? Or am I looking at if there's a choice of diameter and baking temperature that's optimal? Or is there a temperature that works best no matter what size ball of dough I use? Okay? So make your choice, because that's going to change the way you do your experiment. Now, in this particular case on cookies, if I could come up with a temperature that like 1 inch, 2 inch, or 3 inch, that's still the best. That would be ideal, because then I don't have to worry about the effect of the user's visual skills on coming up with the size of the ball of dough. Okay? So we want to know the effect of every factor, but we also want to know if they're independent or if there's an interaction between those various factors. Okay? So if you say that the order of the A times B times N, so 36 experiments in our case, is completely random, then what we have to do is figure out the overall mean plus the effect of the temperature of the size of the ball of dough, the effect of the interaction between those two, and then just random error. And that's going to be this value that I'm going to be estimating. So what I'm looking for is, do I end up with the estimates of the means to be 0 overall? So we're testing that the taus, the effect of oven temperature, is 0. The effect of the size of the dough is 0, or this interaction between them is 0. So this is what we end up doing a hypothesis test on. So to do that, you're going to have to do the two-way ANOVA testing. And yeah, I say we'll return to that. We're not going to do that. Okay. So that's one thing you can do, is you just simply go through and randomize these things and do a complete set of tests. Sometimes you can't completely randomize. Like maybe your oven takes a really long time to heat up or cool down, and so you would need to do everything at a particular oven temperature on one day. You can't get another set of tests in at a different oven temperature on the same day. So in those cases, or maybe your dial doesn't have any markings on it and you can't guarantee that you're coming back to the same setting each time. And so in those kinds of cases, we run our experiment in blocks. So we already know we need randomization and repetition. The other thing that we may need is to do this randomization within a block. So maybe I have to set the oven temperature with this funky dial I have, and then I'm going to change up the size of the cookies and where I place them, and yeah, do those experiments all within a block, because I will never be able to get the oven setting to exactly that ever again. Okay, that's an issue. That's why we have blocking sometimes. But within the block, you need to randomize as much as possible. That modifies the equation. Now, if we are saying that we have a discrete number of choices, so 1 inch, 2 inch, and 3 inch balls of dough, not an infinitely variable measurement there, then for discrete choices, then what we have to do is this factorial approach, 2 to the k factorial. There are programs that actually do this well. You'll want the full course to be able to do much more with this. But the concept is that you sort of start with your corner pieces. So smallest dough and lowest temperature, largest dough, largest temperature, largest dough, smallest temperature, largest dough, highest temperature, or smallest dough, highest temperature. You look at your corners and you get a sense of which direction. So maybe the best quality is up here and the worst quality is here. And so you can infer from that that going this direction is getting you better quality. But then you're going to want to maybe try something in between. Choose some midpoint of these and see, does that really continue to show the trend? Now here these contours are overlaid and we see that they're, not necessarily truly showing the full trend, right? But as you did this, these two are both relatively crummy, okay? This one would be, I guess, if you say green is the crummiest and red is the best, okay? Then the worst is here and the best is here. So you're looking at these kind of with a relative sense, and you can narrow the size of your block so that you can find wherever your optimal value is, okay? You would really want to ideally choose all your corners and then randomly choose a few interior points. So with this very, very, very brief review, Let's go through kind of the checklist for how to plan an experiment. So first you want to prepare a systematic and inclusive schedule that includes randomization. Okay. Then you want to provide for how you're going to go through and perform this experiment step by step. Adapt the schedule if you're needing to. Have a plan for that. And then eliminate the effects of your variables that you aren't studying by controlling, balancing, or randomizing those. So maybe I only have enough flour to make the recipe 3 times, so I'm going to have to use a different batch of flour for the remaining experiments. So if I know that in advance, then I can plan for bringing in the flour, pre-mixing it with the existing flour so that all of them have a uniform mixture. That's one way of doing it. Whatever it is, so I can eliminate the effects of those other variables. So thinking through what those might be. I want to try and minimize the number of experimental runs that I can do in such a way that I will meet my objectives for this experiment. Okay? And then figure out what method of statistical analysis you're going to be needing to do. Arrange for how you're going to, in an orderly way, gather the data. Review the experimental design with everybody else, okay? Usually, if you talk this out with someone else, they will point out the flaws in your plan. So adjust the program if you need to. And then write out the steps to be followed very explicitly and clearly. This all needs to be done before going into the lab. So the major takeaways I want you to have from this, because again, this is such an overview. There's no such thing as a bad experiment. You can poorly design an experiment or you can poorly execute an experiment, but the experiment itself is actually probably good. Okay? You want to control the effects of lurking variables on the response. Okay? So that's things, like I said, like you ran out of flour or something like that. So try to control those. And the most simple way is by comparing 2 or more treatments. You want to be sure always that you randomize. You want some impersonal chance approach, okay, to assign the experimental units to treatments. Okay, not just, I feel like doing this one next. Okay, have a plan in advance. Maybe you had a random number generator create your ordering, or maybe you're flipping coins. Okay, but randomize. You want to replicate, so you always want to do repetition of your treatments as many times as you need to so that you minimize that error. 3 to 5 times is typically a minimum that you want to do on any of our experiments. And then an observed effect so large that it would rarely occur by chance is statistically significant. So that's what you mean when you're identifying something as statistically significant. So that concludes our brief introduction to experimental design. Again, replicate, randomize, and minimize those lurking variables by having a good plan in your experiment. So thank you very much.